So let's begin this session. Our first speaker is Petr Siegl. He'll be talking about the damped wave equation with unbounded and singular damping.
Thank you very much for introduction. And first of all, I would like to thank the organizers for all the efforts to run this conference, which is great, and also for the hospitality of the center. I'm very pleased to be here. It's my second time in Bangalore, not here, but second time in this area. So today I will speak about the damped wave equation with unbounded damping. So no Schrödinger operators or Schrödinger equation, but due to the damping, this problem is very non-Hermitian. I will explain why. And actually, technically, the main point is to know something about Schrödinger operators with complex potentials. Basically, everything what I'm going to say is based on the paper with Pedro Freitas from Lisbon and Christiane Treter from Bern. And at the end, I will mention something that it is in the paper with my student Ahmed Arifovsky in Bern that should hopefully appear on arXiv very soon. So this is the outline of my talk. At first, I would like to recall some basic concepts in wave equation with damping. Then the core of my talk will be actually examples. I will try to explain everything on examples. And then last part are results. So I'm mostly mathematician, so results, I mean theorems that we could prove. But I will try to skip all the technicalities and all the subtle points. I will try just to explain what are the claims, and I hope that these examples that I will discuss quite extensively will help to understand what I'm talking about in the last part. Okay, so what do I mean by wave equation? What is the setup? Let's omega be some domain in Rd, and x, the spatial coordinate, lives in omega, and we have this partial differential equation. So it is utt, second order in time. Here is Laplace of u, so this is standard wave equation. Then, for some reasons, I sometimes want to include also potential. Q is a real function, non-negative. But the main term I'm interested in is the following that is highlighted. It is 2a of x multiplied by ut. And this is exactly the damping term. So t is time coordinate. I will be interested only in positive times. X spatial coordinate a is a damping. It means real function, actually non-negative. If I would go to negative, it would be gain of energy, but I will be talking only about damping. And Q is potential. I should certainly equip such problem with some initial datum. So I have some, in principle, initial conditions living in suitably chosen spaces. And in case my omega, where spatial coordinate lives, has some boundary, I should impose boundary conditions. And in my case, it will be always Dirichlet. Now, if you look into literature, there are hundreds of papers about damped wave equation. For example, in this paper, you can find many references. But what is the point there? Almost exclusively, damping is bounded function. Or it is unbounded, but it is in some sense small with respect to the Laplacian. Typical case is that damping can be singular in a finite point, but not too much. It must be controlled by Laplacian. I won't go to the details. My point will be that I will have damping that is unbounded and is completely not controlled by Laplacian or anything else. You cannot view this problem as, in any sense, as perturbation theory. Now, yes, I get to there. But okay, I have T only positive, and yes, of course, I will get something with problem with Schrödinger equation. Now, the way how I want to solve it is to use semigroup theory. It means I want to find solution as exponential of something. This is second order equation in time, and a standard trick is to rewrite it as a first order system. So this is exactly what is written here. What I do, I call V. V is equal to ut, this is the first equation, and then I have this first order system for u and v. And g is generated then of the semigroup, so this is exactly like Schrödinger form, if you want, of the equation. I have dt of something is equal to h or G of something. And I want to solve it or say something about the existence of the solution, how they behave. And certainly one way how to do it with linear equations is to look into the spectrum and properties of this operator G, what we always do in quantum mechanics or wave equation, heat equation, whatever you like. Now, I have equation, fine, maybe I have initial boundary conditions, but I should also fix functional space where I'm working. And the choice here is up to me. I can select whatever I like, but there is a good reason to select following space. Second component is just L2. First component is a bit more complicated. In simplest cases, this is the first Sobolev space, but it can be a bit more general. The point of this space is that these are functions such that if you take the derivative, it is square integrable. And if you have some q potential, also integral of u squared times q should be finite. So these functions u, they live in a space, and this is this w of omega, such that this norm here is finite. Now, why is this space natural? There are many reasons, but maybe from mathematical point of view, the most natural is the following. If there is no damping, so here is 0, this operator becomes symmetric if I multiply by I. So I times G is symmetric with respect to this product. So this product is, here I have derivatives, there should be Q, and in the second component is just L2, and all these brackets are L2 products. So without damping, up to I, that is irrelevant. I'm in perfect self-adjoint situation if I work with Harder and explain that this problem is self-adjoint. And I know everything about it in principle. But once A is non-zero, it completely breaks down and I can never have anything symmetric. So this is the way how non-hermiticity enters. Now, why is there some connection to Schrödinger equation, or how can we solve the problem for eigenvalues? Well, let us try. So to solve eigenvalue problem, we should solve this equation, lambda is a spectral parameter. This means we should solve these two equations. But the first one is very simple. V is just lambda u, so I can put it into the second one. And what I get on the left-hand side, if I fix lambda for a moment, it is Schrödinger equation. So I'm solving actually the eigenvalue problem, or spectral problem, for this T lambda, and T lambda is what? Is Laplace Q and 2 lambda A lambda squared. And this is certainly something minus Laplace plus function, so Schrödinger operator. But what is the difference here? This is T of lambda. For every lambda, I have Schrödinger operator, and my lambdas are all points in C. So here, for complex lambdas, this part will be complex. And if A is big, then I have here big complex potential, or unbounded complex potential. And my problem is what? Is to find lambdas for which I have eigenvector corresponding to eigenvalue 0 of this T lambda. So if you rewrite it, this eigenvalue problem, sometimes it's called quadratic pencil or quadratic operator function, means that lambda is in spectrum of T if, by definition, 0 is in the spectrum of T lambda. T lambda is already a fixed lambda. So here it is already standard spectral problem for operator. So this is natural generalization of spectra of operators. If you think about operator A, what it means lambda is in the spectrum. Equivalently, lambda is 0 is in the spectrum of the operator function A minus lambda. Here the difference is that my function is quadratic, not linear. Okay, so of course, this is no surprise that such equation comes, because if you from the start insert these answers for functions for your solutions, e to lambda t u of x, you get exactly this problem. So what I mean by that, if this function is a solution of, or this function is a solution of time-dependent wave equation, if and only if this solution, this equation for u and lambda is satisfied. Okay, so let us have a look on a very simple example now. What I will talk about now is setting one-dimensional on interval, so my omega is minus 1, 1. I have no potential, and my damping is just constant, A naught. It follows by standard arguments that there is nothing else in the spectrum than eigenvalues. So everything what I was saying up to now, I can do without problems. So what it means, if I think about it, this applied on U should be 0, I can rewrite it in this way. So minus U double prime should be some number times U with Dirichlet boundary conditions. But this is exactly the Dirichlet problem. This is the square well problem. If you think about this, there's a new spectral parameter mu. This is exactly a square well problem. This we know. These are the eigenvalues of Dirichlet Laplacian on minus 1, 1. But there is a relation between lambda and mu, which comes, this I call mu, so it's written here, which we can solve for lambda, and this is what we get. So now I plotted a few of these solutions of these eigenvalues so that it's clearly visible what I mean by this. So mu n are basically n squared. Forget about them. Pi and 2. So if there is no damping, A naught is 0, then eigenvalues are plus minus I square root of this, which is n. Then I have eigenvalues on imaginary axis. Here is 0, this is imaginary axis, real axis. And this is perfect, exactly as I wanted. I said that if I multiply by I should get something symmetric. So if I don't, my spectrum is on imaginary axis. Now, when I turn on the damping, what happens? There is a shift in eigenvalues to the left. So this is, let's say, the first damping that I put, which has value like 1. And then there's plus minus this square root. So first eigenvalues are here. If I put more damping into that, it's kind of the same. I shift more. But what happens here I have basically integers, and if A naught is big, for first few eigenvalues, this will become negative. Square root of negative is imaginary, so altogether it will be real. And what you can see in the picture, I have infinitely many on the vertical line, but then I have few black balls here on the real axis. If I damp even more, everything is shifted and I have more of these red now eigenvalues. What is the essential point here? And it's quite simple. Some of these eigenvalues, they are more to the left. Infinitely many are here, but some go to the right. And more damping I put, the closer the rightmost eigenvalue gets to 0. So this is a well-known effect of overdamping that is known also in classical oscillator, if you want. And this is inherent and in these damped problems. It is not true that if you put more damping, then general solution is decaying faster. So how you can see this? Well, there is eigenvalue that is almost 0, and I said that these are solutions of this type, e to lambda t u of x. If you think about norm of that is determined by the real part of lambda. If real part of lambda is almost 0 but negative, yes, I have exponential decay, but slower and slower, closer I get to the imaginary axis. And I wanted to show you a little animation that you can find on internet. So this is exactly this case. I have some initial datum, and I let it evolve. Now damping is something like 1, and you see, well, it's what it should be. It's like a wave, and it gets damped. Now, I will stop it and put it back, and I put damping to maximum what is allowed here, like 20. And it is kind of the same, but difference is that it is still damped, but much, much, much slower. If I freeze it in time, and if you look on when I will decrease now the damping, then I see that actually decreasing of the damping means that solution decayed faster. Okay, so all of this is, of course, well known. But one should have it in mind that it is not so trivial that more damping gives better decay rates. Now, this was really simple. This is exercise for students. But what if I put there not constant damping, but function. For bounded damping, there is extensive literature again, and I want to show only very few results here. If I'm still on finite interval minus 1, 1, and I put bounded damping, what can be proved is that eigenvalues are on vertical line. Shift is actually the average of the damping. So I'm in this situation, and then I have some corrections. So asymptotically, I'm basically in the previous pictures. Moreover, and this is quite important, it can be shown that eigenfunctions form a nice basis. They form Riesz basis. So in terms of this conference, I have metric operator that is perfect. Of course, I cannot map my problem to self-adjoint, but I can have it quasi-normal. I can map this operator to normal operator. Then if you think about decay rates of the general solution, it is here indeed true that decay rate of the general solution of time-dependent problem is indeed determined by the position of the rightmost eigenvalue of the problem. These claims are true even if damping is L2 or maybe even L1. Now, sorry, I don't know what happened. It seems that life is perfect, but not really. Now I'm getting to the point. What if I leave these safe assumptions? What if I allow that my damping is unbounded, is singular, whatever? I want to show one example of the singular damping, then I will speak only about unbounded, I mean unbounded at infinity. But I want to show this one that shows it's really different. So now interval 0, 1, Dirichlet conditions and damping is 1 over x. This is clearly not L1. But the spectrum of what we are looking at is discrete. That can be shown by operator theory. But actually it is empty. So there is nothing in the spectrum. No eigenvalues, but no continuous spectrum, nothing in this case. And you can go even further. If you look on a time-dependent problem, it can be shown that every solution vanishes in finite time, which is larger than 2. This was proved by Castro and Cox. So once you lose these safe assumptions, really strange things in some way can happen. Maybe this emptiness of the spectrum can be naively understood in this way. Here was average of the damping for non-L1 function. This is infinity, so maybe I can think everything is shifted to infinity, but this is not that easy. But anyway, this can be shown in this example. So some very naive intuition may not work here. Now, my main point is something else here. I would like to look on examples and problems of this type. Let my omega, so the domain where x lives, be R, so now unbounded domain, and I take dampings like x to 2n plus a0. So maybe you can have in mind it's a little bit like harmonic oscillator for n equal 1. So that's the idea. Well, we can have a look on eigenvalues. So we have this eigenvalue problem. And in fact, by tricks and procedures that many people do here, you can solve this problem. So what is here? What is the problem? It looks like Schrödinger equation, but it's always a bit bothering that there is lambda in front of potential. But in this case, you can get rid of it. How? You rescale your x to complex plane, and you get rid of lambda, and you convert this problem actually to some Schrödinger problem. And this is exactly what you do, and you get the following formula. And it is completely explicit. So now let me explain. So the point is that eigenvalues for this damping are given in terms of eigenvalues of self-adjoint operator, Schrödinger, minus second derivative plus x to 2n. These are mu case, so this is here. And they come with some phase and with some power and some corrections if you have constant damping there, and there is some remainder. Eigenvalues of this, of course, are well known, especially for n equal 1. This is completely explicit. So here you get, if a not equals 0, you get here just formula. Now, if you plot it, you see the following. Blue balls are for n equal 1. Then this is maybe n equal 4. This is 6 or something like that. So what is interesting here, these eigenvalues, they are on the race. Although here on this level, their spacing is either constant for harmonic oscillator or grows, because of these powers, these eigenvalues, they accumulate at infinity. And then the angle here is determined by power here. And as you increase n, this angle becomes bigger. So you go closer and closer to the imaginary axis. Now, this might be not a big surprise. Why? Let us think about it very formally. What happens if I send n to infinity? If I am with x in between -1 and 1, I'm taking something small to infinity, which is 0. If I do this outside, it is infinity. So what I can expect that these eigenvalues actually converge to the problem that lives only on -1, 1. If damping, that is in this case, because this in this interval tends to 0, is just a naught. You have some pictures and formulas you can check, but the question is, can you prove that? Well, maybe there's some hope, because if you look into the Schrödinger case, this is exactly what you can prove. If you have x to 2 and potentially L to R, you can prove that this converges in suitable sense to the square well with Dirichlet conditions. And you can also guarantee convergence of eigenvalues and eigenvectors. What is a bit complicated here, you are talking about convergence of things in different spaces. But there is a technique how to deal with that. Okay, now maybe you got some feeling what can happen in case of unbounded damping, that we no longer have vertical lines, and these asymptotics can be quite different. It depends on what happens at infinity. But if you go to more dimensions, you will see immediately that there is not much intuition that you can expect. So what I would like to show now, very fast, is two-dimensional strip with damping that is x squared along the strip, and there is some constant damping background. If you solve this, this is the plot with eigenvalues. So you have many sequences, and it's well, it's based on some explicit calculations. You can describe how they go to infinity, but certainly, basically, whole left complex plane except this sector is full of eigenvalues. This is something that you probably cannot guess if you look on the problem. Okay. Now I would like to go to the final part of the talk. So what can we actually show? What can we prove? Well, the basic problem that it is in this business was maybe the hardest part is to actually show that the solutions of this problem exist. And it is unique if you want. So this can indeed be done. I don't go to technical assumptions. I just say that I need that damping is sufficiently regular. I need something like C1 and not too wild growth at infinity and not too wild oscillations. Under these assumptions, you can prove that indeed the solutions of the wave equation exist. This is for whatever dimension, whatever domain omega in RD. And it is indeed a semigroup, contraction semigroup. So at least you know that solutions do not explode. Then what you can prove, and this is also not that easy as for eigenvalues, that indeed the spectrum of G, of the generator of the matrix, is related to the spectrum of this operator function. There is indeed equivalence. But what I want to mention here, this equivalence holds only for complex points without negative real axis that I didn't touch so far. There is a slight problem here. And in a case my damping is indeed unbounded at infinity, then everything else outside negative real axis can be only eigenvalues of finite multiplicity. Now, the next claim is what can we do in case of this diverging damping to infinity. If we are in this situation, we have sequence of damping such that on some subdomain we converge to something finite in suitable sense. Outside we converge to infinity. Then indeed we can prove that complex eigenvalues converge to the limiting operator. It means two things. Every eigenvalue of the limit is approximated by eigenvalues of the sequence, and also the other direction, there is no pollution, meaning if I look on accumulation points of these approximating eigenvalues, and if I find finite accumulation point, then this accumulation point is in the spectrum of the limit. This does not exclude that something can go off to infinity, as it was in Westock. Many things can go to infinity. But this is the best possible spectral convergence you can hope for here. So all these pictures that I was showing, you can actually prove them. And also, of course, convergence of corresponding eigenfunctions. Now, what I deliberately left out so far, what happens on the negative real axis? Well, there is a problem. If you think about it, for example, let's take lambda equal -1, then what is our function? It is minus second derivative, and then comes something like minus 2x to 2n. So if you want inverse sine, harmonic oscillator or whatever. And spectra of these and properties of these are quite different to something here, even if it is complex. So for example, if you look on inverse sine, harmonic oscillator spectrum of that is whole R is continuous. If you look on higher powers there, it's more complicated. It goes to the talk yesterday about 1/x². You need to fix self-adjoint extensions. There are many. This is not in a limit point case. But any self-adjoint extension has discrete spectrum, which is unbounded from below and unbounded from above. So to get some intuition out of that is quite difficult. And actually, this is not the way how you can do it. There is indeed a problem on negative real line that I'm not going to touch. It's a little bit technical, but if you do it directly for G, for the matrix, you can get the following. And this is a simplified version just for dimension 1. If you look on this lambda-dependent potential, which is there, and I put here minus, and if it happens that eventually for large x, this is increasing function, and it limits its plus infinity, what it means, lambda is here negative, so what I want that this A damping beats everything else. So if you can forget about Q and if you can forget about lambda, if this A is bigger at infinity than the rest, then this is satisfied. And if some growth condition is also satisfied, this is technical, then such point is in the convergential spectrum of G. This you can extend to more dimensions. Actually, it is enough. There is some channel even shrinking in your domain, where something like this holds. So damping goes to infinity and it beats everything else at infinity. Then such lambda is in continuous spectrum. What actually happens in our examples? Well, if you apply this, you will easily see that you can do it for all negative lambdas. And what happens that actually whole negative real axis is in the essential spectrum of these problems. So what I was hiding from you up to now is this part of the spectrum. So we have some complex eigenvalues that are perfect, that comes from Schrödinger's with complex potentials. But with unbounded damping, we always get whole, not always, but under those assumptions, we get negative real line in the continuous spectrum, and it touches 0. So in this way, this is also an effect of overdamping, if you want. We put too much to infinity, and what happened, the spectrum actually touches 0, which prevents exponential decay of general solutions. It is never here. If you want to get rid of that, it is possible, and this is done typically even in case of bounded dampings. You can add some potential Q. In case of bounded damping, it's enough to put constant, positive constant potential, and everything is fine. All these pictures are shifted to the left, and we are happy. But in this case, this is not enough. To shift essential spectrum to the left, you need to put potential that is stronger at infinity than your damping. So, for example, something like that, 2x² and x². Then you can indeed shift it to to the left. If you put here something like x4, then you can actually get rid of the essential spectrum completely. But it is you are paying the price. You really need to have really strong potential in the problem. Now, this maybe you should also compare with the limiting behavior. So I said that these problems x to 2, and they converge to something on minus y1 with damping just a constant. Here, the decay rate is never exponential. In the limit, I have perfect exponential decay. It's something like a0 over 2 will be the decay rate in the exponential. So there is a clear jump in the limit when you speak about decay rates. Now, in fact, it was completely independent and a very recent paper. These two Japanese authors, they looked on similar problems, unbounded damping in RD with comparable assumptions, and they could get some estimates of the solution. And what they got is polynomial decay, no exponential. It is absolutely unclear if this is optimal or not, but there is some decay. Okay, and now the last part that is related to the second paper I mentioned. We now hopefully all know that in many PT-symmetric problems, there are always issues with pseudospectrum. It means for cases we have only eigenvalues, there are always problems with basis of eigenvectors. If I calculate the basis, is it, or eigenvectors, are they actually basis or not? And it's not clear at all. And in this IX³ and everything similar, it is never the case. So what happens here? I just recall this notion of pseudospectrum. For every epsilon positive number, I define set sigma epsilon of G, which is the spectrum, fine, but also the points Z in complex plane for which norm of the inverse of the resolvent G minus Z inverse is larger than 1 over epsilon. So if you want, if you think about matrices, spectrum are those points where we have singularity of the inverse, and these are the points where the inverse has big norm. What is interesting about this set, many things. You can conclude things like there is no basis and there is no solution for your problem like IX³. You cannot solve this problem. A time-dependent equation in L2. It is ill-posed. You get it from looking on objects like that. But what I want to mention here, this is already interesting because it tells you how your operator respond to the small perturbations. Because these sets are actually equal to union of spectra, not pseudospectra, spectra of operators G plus V, where V is a perturbation with norm smaller than epsilon. So naively would expect I perturb a little, eigenvalues move a little, but what happens in these cases, in many PT-symmetric cases also here, is not true at all. You perturb a little, but you can completely change the position of the spectrum. And this is the picture of pseudospectrum that I would like to explain. It's for damping x². So this is complex plane. Here is imaginary axis, real axis. Black balls are eigenvalues, so this is what I showed you. Here is already some numerical mass. This is the essential spectrum. It's this. Everything is done for truncated problem, and these contours are actually level lines of the norm of the resolvent, and it's coded in colors, and it's logarithmic scale. But what you see here, here are the eigenvalues. But as you go basically on every line, any line like this or like that, you cross all these level lines. So norm of the resolvent should grow. And what it means again, it means that if I start to perturb this problem, then these eigenvalues can be moved inside of these huge sets. You should think about it as like almost quadrant or something like that. You can describe the shape of this curve, but it's like quadrant. So this eigenvalue can be moved somewhere here by perturbation that is of order 10 to minus 12. Okay. So the question is, of course, this is numerics. Can you prove that? Yes. And this was the work of my student, his master thesis. So this is very simplified version of what he could get. In on dimension, omega is r, and in case there is no potential and damping behaves like x to 2n, then as you go on any line to infinity, I exclude this line, where is the spectrum? If you go along any line, norm of the resolvent goes to infinity. So there's indeed this issue with pseudospectrum, maybe always when you have a lot of non-hermiticity, like unbounded potential, unbounded damping. And in particular, from these pictures and that proof, you see that there is no way how this operator could be similar to normal, how these functions can be basis in their own span, and so on. So thank you for your attention.
You said that there is a way to convert your operator into normal one by the mapping, which has some reasonable properties. In my eyes, that's a metric which in space introduces new geometry. And in this geometry, you cannot use this norm in this right-hand side expression. You must use the norm in this space, because it's the only space where your physics lives.
Of course, but here I give a very good reason why to consider my norms. Because what is behind my space is not only that something is symmetric, but this is what comes from physics. This is an energy norm. So when I'm talking about decay of solution, I'm talking about decay of energy. I'm not talking about arbitrary norm that I select. Of course, I can pose equation in whatever space I like, and I can make some claims. So this is the claim about the energy norm.
I agree that in that norm, everything is correct what you said, and it's physics, because it's not this transition to normal operators which is useful or needed. But I'm speaking about situation where this transition to normal operator defines some physics.
Yes, of course.
Then you must be very careful with statement like that.
Okay. Any other questions? Okay, so let's thank the speaker again.